Welcome to AI Unleashed, your place for innovation, news and all things artificial intelligence. Hit the like button and subscribe. While the hype on large language model, LLM, is still iron hot in the industry, the leading research organizations have turned their eyes to multimodal foundational models, models that have the same scale and versatility characteristics as LLM, but can handle data beyond just text, such as images, audio, sensor signals, and so on. Multimodal foundational models are believed by many to be the key to unlock the next phase of artificial intelligence, AI, advance. We take a closer look at how Google approaches multimodal foundational models. The content covered are drawn from the key methods and insights of Google's recent papers, for which we provide references at the end of this article. Multimodal foundational models are exciting, but why should you care? Perhaps you're one of the following: an AI, ML practitioner who wants to catch up with the latest research development of the field, but you don't have the patience to go through dozens of new papers and hundreds of pages of surveys. A current or emerging industry leader who is wondering what's next after large language models, and is thinking about how to align your business with the new trends in the tech world. A curious reader who may end up being the consumer of current or future multimodal AI products, and wants to get a visual and intuitive understanding of how things work behind the scenes. For all the above audiences, this information will provide a good overview to jump-start your understanding of multimodal foundational models, which is a cornerstone for future more accessible and helpful AI. One more thing to note before we dive in: when people talk about multimodal foundational models, they often mean the input is multimodal, consisting of text, images, videos, signals, etc. The output, however, is always just text. The reason is that text is the most generic form of communication format. If we can output text, we can output code and feed it to downstream tools to generate whatever multimedia formats desired. Not to mention there are many AI tools nowadays that take natural language as input and generate images and sounds. The first format to incorporate is text, or in research terms, language. Researchers like to call it language because language implies that the text is drawn from a linguistic system with a coherent semantic meaning, be it any natural language, code, commands, symbols, and so on. In layman's terms, we'll just call it text in this video. There are a lot of materials online about building large language models, so we won't cover it in depth here. Just note that Google's recent results on LLMs and multimodal foundational models are all built on Palm. If you're not familiar with it, just think of it as a black box similar to ChatGPT, though their internal mechanics vary quite a bit. The fundamental concept to grasp here is that the input text is broken into tokens. Each token is then mapped into an embedding space. Effectively, each token becomes a vector. Then the list of the vectors are fed into a model consisting of layers of attention-based networks. The output of the model is also a list of vectors, which can be converted back to tokens, and then concatenated to form the final text output. The model has hundreds of billions of parameters, and is trained on a massive amount of text data for some simple prediction tasks such as given a text prefix, and predicting the next token. The resulting model will need to go through further fine-tuning to become more directly useful. For example, Google has adapted its Palm model to the medical domain and created MedPALM. You can reference this article for more insights on how to adapt a large language model to your specific domain. At this point, we have a large language model. The next step is to incorporate other media formats. To incorporate images, the first thing to do is to convert an image into a format that can be processed by the large language model. Because we already have the large language model and we want multimedia to be processed uniformly, the natural choice is to convert an image into a list of embedding vectors. Recall that text is also converted into a list of embedding vectors above. Obviously, the vectors from image and text should all have the same dimension. Google has done impressive work in adopting transformer architecture for image processing. That turns out to be a great fit for the image to vectors conversion. Concretely, every image is resized to 224 x 224 resolution, and then broken into 14 x 14 pixels patches. This results in 224 x 234 divided by 14 divided by 14 equals 256 patches. Each patch goes through the same learnable linear transformation to transform into a vector. Each vector is concatenated with a learnable positional embedding. These concatenated vectors are then fed into a transformer model. Google Research called this model architecture V, Visual Transformer. The output of the V model is also 256 vectors. A shallow network is then attached to the output vectors from the V model, and the whole architecture is trained for image classification, image captioning, and other image processing tasks. See Figure 1 for an illustration. Figure 1. Illustration of V architecture. Once the image processing training is done, throw away the shallow network on the top. We can use the 256 output vectors from V as the embedding representation of the image. The core idea is that through large-scale training, the V model has learned to represent the input image by a list of vectors that can be easily used as input features for a variety of image processing tasks. One special note here is that Google Research found that V's results on image processing is superior to state-of-the-art CNN. They attributed the superior performance to the scale. Transformer-based architecture is known to scale better, and the fact that attention can happen directly between any two input patches early on in the network. This image representation learning done in V is transferable to multimodal settings, as you guessed it. The output vectors from the pre-trained V can serve as input to the large language model. For an input prompt such as "what happened between" and the words are converted into embedding vectors for the large language model as usual. Each image is converted into 256 vectors using V. All the vectors together form the input to the large language model. Finally, the large language model is fine-tuned end-to-end, or by freezing its various parts, on multimedia training data, and the resulting model is the multimodal foundational model. Figure 2. Illustration of multimodal foundational model architecture. Obviously, the dimension numbers mentioned above are just one configuration Google Research's papers used. You can try your own if you want. But be aware that the V output vector dimension should match the larger language model input vector dimension. If different, you can adjust either models, or you can insert a linear transformation between the V output and the large language model input to squeeze or stretch the V output to match the large language model input dimension. Now that we know how to incorporate images, we can employ a similar scheme to include other media types. They don't necessarily have to use a transformer architecture. Google Research employed a multimodal foundational model in robotics, 7, by converting states, objects in scene, and other input sources into the same vector embedding space. Many of those input formats are actually converted to the embedding space using very simple transformations. Google Research has also recently adapted the methodology to the medical domain and created a multimodal foundational model for healthcare. 8. Figure 3. Illustration of multimodal foundational model use cases in a. Robotics and b. Medical field. In this video, we had a glimpse of where the bleeding edge is in the field of multimodal foundational models. The core idea is twofold: sad face. 1. Encode multimedia in the same embedding space so that they can be processed uniformly by LLM architecture. 2. Stitch together large pre-trained models. They are often pre-trained in unimodal settings, and fine-tune with multimedia training data. Some of Google Research's recent breakthrough really starts to resemble an AI agent that people would want and could use in day-to-day life. While there is still a long way to go for more accessible and helpful AI, there is no doubt that multimodal foundational models are the inflection point of AI, and future development is going to be ever more exciting. Thanks for watching.